Alright guys, welcome back. In today's question, we have another question from chapter 3, and we have these uniform rectangular plate with mass of M that is suspended by 3 cables AD, BE, and CF, and we need to determine the tension in each cable. So let's start with the free body diagram. I'm just going to show it on this figure that we have in here. So before that, let's set up our origin first. And if you put that origin at point B, let's consider this as positive side for Y. This will be our X, and we'll consider this as our Z. And for doing this, first of all, we need to find each tension in the cables in a unit in a vector form. And let's see what we have. So we have the tension here, let's call it TAD. We have the tension in the cable BE, and we have this tension in here, let's call it TCF. And obviously we have the weight of the slab, the weight of the plate, which is rectangular, and the central would be exactly at the center. And if we want to find the weight, we simply have mass times g, or acceleration of gravity. That's pretty much all we have. Again, this will be exactly in the center. Now let's start with the first tension. So we have the TAD, and if we want to find TAD, we simply have to do the magnitude times the unit vector, and we covered that in previous questions, how to find the unit vector. And all we need to do is basically the vector AD divided by its magnitude. So let's start with this. So for TAD, we have to find the coordinates of D and subtract that by the coordinates of A. And if we look at this, we'll see for X components, since AD is in YZ plane, there is no X component. Looking at the Y, we'll see that we are moving 0.3 meter toward the positive side of the Y, which means we have for AD we have let's consider this as the positive side for Y. And if we do that, we'll see that now that we consider our Y in this direction, we are going in the opposite way of Y axis, which means minus 0.3, moving from A to D. And if we look at the Z component, we'll see that we are going 0.8 meter toward the positive side of X. And what we have at the bottom of the ratio is simply 0.3 squared plus 0.8 squared. And if we calculate this, we'll get the 80 times minus 0.35 for J and plus 0.936 for K. So if we look at TAB, we'll see that actually AD and TBE are symmetrical about this line because they are at the same distance, and they just have different direction for Y, and the Z would be the same. So we can go straight with what we found for TAD, and we can see that the Y for TAB will be positive. But let's just for the sake of practice, go with the unit vector again. So again, we are in the YZ plane, no I component. And this time, since moving from B to E, we are having this 0.3 and it's toward the positive side of Y. We'll have a positive 0.3 J, and our K will be the same. And again, we have the same magnitude as AD for the unit vector. So TAB would be simply what we found for TAD. This time only the J component is. And if we want to find the unit vector, find the TCF in a vector form, we see that we only have a Z component, and it will be toward the Z axis, and it will be positive too. So for TCF, we simply have the magnitude, and K, we have the same thing for the weight. And this time, since we are in the opposite direction for K, we only have a negative. So we have all the forces in a vector form now. And now we can move on to our equilibrium equations, and we can start with the moment. So since we are in equilibrium, the sum of all forces equals 0, and we have the same thing for the moment. about any point that we want to consider. So if we look at fz, so let's start with the moment of, let's find a moment about y-axis. Let's see what we have for moment of all forces about y-axis. So let's start with the AD. Looking at the AD, we'll see that it cannot make any moment about y-axis since it's along the y-axis, and we have the same scenario for BE, but we have the moment of the weight, which the distance for y-axis would be 0.8 divided by 2, which is 0.4. And we also have the moment of the TCF, and distance for that one would be 0.8 meter. So let's go with the mg first. So if we look at here, what we have, we previously covered this in the previous question. If we look at here, we'll see that the moment of mg will be in this way, which is clockwise. So we get a negative sign for mg, and as I said, the distance was 0.4. And if we look at the moment of the TCF, we'll see that TCF will be a positive since it's counterclockwise about y-axis, looking at the y-axis from this little guy that we have in here, and the distance would be 0.8 equals 0. And from here we can figure out TCF is half of the weight. So that was the first equation. Let's move on to the moment about x. And if we look at the moment about x-axis, we'll see again we have the moment of TCF, we have the moment of mg, and we have the moment of a y component of z component of TAD. So let's start with the TAD, and we found already the z component is 0.936. So we have, and if we look at the, again, we're looking at the x-axis from here, and we'll see that the moment will be clockwise, so we have a negative sign for z component of AB. So 936 TAB, and let's figure out the distance. And if we want to find the distance, we'll see we have the length of this lab, which is 0.3 plus 0.3 plus 0.4, which is 1. So we also have the moment of TCF, again negative, minus TCF, and the distance for CF this time will be this distance, 0.5 to x-axis. And the last one, mg, since it's in the middle, again we'll have mg, and since it's counterclockwise, we have a positive sign, 0.5 equals 0. And from the previous part, we know the TCF is already half of mg, and from here we can find TAD, which will be so this will be, so we have TAD in here, we'll get TAD 0.267, wait, and that's that. So we have two of the unknowns. If we go straight with the sum of all forces in z-axis, we can find the last tension in the cable, which from the symmetry of this slab, from the symmetry of this plate and all the tension, we can figure out that we have to get the same magnitude for the tension in BE2, but let's just find it for the sake of practice. So what we have in z-axis is the z component of AD, the z component of BE, and TCF, and minus mg. So we have TCF minus mg plus the z component for TAD. So we have TAD 0.936, and we also have TBE, which is what we are looking for, again 0.936, equals 0. We know each of TCF and TAD from the previous step, and if we do that, we'll get TBE 0.267 mg, which is what we had for TAD. And that would be the final answer for this question.